Okay, guys, welcome. Today we're going to talk about rational functions. So I want to be able to look at rational functions in such a way that we know how to manipulate rational functions algebraically, and by that I mean to add, subtract, multiply, and divide two rational functions. I also want to talk about how to do long division with polynomials or with a rational function, and it will also talk about how to look at end behavior of rational functions and look at asymptotes as well. Okay, so first of all, what is a rational function? Well, a rational function is essentially a fraction where the top and the bottom of that fraction are both polynomials, right? So both of these are polynomials. And of course, we require that since q is in the denominator, q cannot be the zero polynomial. All right, but we sort of assume that that's true in most cases. Now, of course, since we have something in the bottom of a fraction, we have sort of this potential domain issue, right? So we also don't want x values that make q of x 0. Right, because then we have an issue. We have a domain issue, of course. So this first example is going to sort of call attention to that, right? So we want to find the domain of each of these rational functions here, of r and of s here. So r of x is 3x to the 5th plus x to the 4th minus 6x to the 3rd minus 2 over x squared minus 9. Now, of course, to find the domain, we want x squared minus 9 to not equal 0, right? So, of course, we look for when it is 0 and sort of toss those out. So we want to solve x squared minus 9 equals 0. Well, of course, we could add the 9 to both sides, and then we get x squared is equal to 9. So once we square, we're going to get x is plus or minus 3. Right, so those would be bad x values, so my domain would be everything but those. Right, so I have minus 3, I have plus 3, I have an open circle on each, and I want everything else. So you could also say in interval notation that this is negative infinity to negative 3, parenthesis, and then parenthesis negative 3 to positive 3, and then finally from 3 to infinity. All right, but the idea is we don't want plus or minus 3. All right, now if we look at s, so for s of x, we have x to the 3rd minus 6x plus 5 over x to the 4th plus 9. All right, and similar here, we just don't want x to the 4th plus 9 to equal 0. Right, but of course we're sort of bailed out because if we solve x to the 4th plus 9 equals 0, of course what's going to happen is we get x to the 4th equals negative 9, and as soon as you try to solve it, you would have to take an even root of a negative number. So this, of course, has no solution. So the denominator is never 0, which is good. So denominator is never 0. So the domain is everything, right? So we could say the domain is fancy R for all real numbers, or we could just say it's minus infinity to infinity. All right, either one of those would work. So it's important that if you're looking at a rational function, you're able to find what the domain of that function is. Okay, now, next what I want to talk about is, so given these two rational functions, so 2x over x squared plus 1, and s of x, which is 3x plus 2 over x to the 3rd plus 5, we want to find r plus x, or r of x plus s of x. Right? Now, before we do that, I want to remind you how you can add just two regular fractions, right? All right, now when you add fractions, if you want to do something like 1 over 4 plus 3 over 4, their denominators are already the same, so we just add the tops, and then we simplify whatever we have left, right? So if you want to add 1/4 plus 3/4, you would get 1 plus 3, which is 4, over 4, which is 1. Now, if you want to add two fractions that have different denominators, then what you need to do is find a common denominator, right? So in this case, you'd have to multiply top and bottom by 2, and you get a 2 over 4 plus 1 over 4. Now we're in the same boat as before, where you just add the tops now. All right, so that's sort of the logic that we want to use here, right? So we want these two denominators to be the same, and of course they're not in this case, but if they are not, then we just multiply them by something that would make them the same. Now, there are several tricks that you can use for this. Like one trick is to completely factor both denominators, and then you can sort of figure out what the other one has that the current one needs, and then the same for the other one, right? Now, in this one, you can't factor either denominator. So the best that we can do is we're going to multiply the top and bottom of each fraction by the denominator of the other one. So this one, I need an x to the third plus 5. And in this one, I need to multiply by the x squared plus 1. So here, now I can write them all over the same denominator. I can write them all over x squared plus 1 times x to the third plus 5. And now I have the 2x times x to the third plus 5 plus 3x plus 2 times x squared plus 1. All right, and now what we have to do is we can distribute and combine like terms in the top. And what's going to be helpful here is we want to leave the bottom factored. So leave this factored. Because remember, when we did something like this, we got to this 4 over 4, a lot of times it's possible to simplify it further. And that's going to be easier to do if you leave the bottom factored. All right, but if we do this, so if I multiply 2x times x to the third, I have a 2x to the fourth plus and then a 10x. And then we're going to get a plus a 3x to the third plus a 3x plus a 2x squared plus 2. Of course, all of this over our x squared plus 1 times x to the third plus 5. Okay, so now we can combine like terms in the top, and we have a 2x to the fourth. Looks like we just have the 3x to the third, 2x squared, and then I'm going to get 10x and 3x, which is a 13x, and then plus 2. And then this is all over x squared plus 1 times x to the third plus 5. All right, and again, usually you can leave that bottom, the denominator in its factored form. Usually that's what's most preferred, but the top you would want to distribute out. Now, in this case, the top doesn't have any easy way to, or obvious way, I should say, to factor it. So we're just going to leave it. If you could factor it and cancel some stuff, that's what you would want to do. But in this case, it's not entirely obvious how to do that or if it can be done. So we can leave it this way for now. Okay, so now in the next example, we're going to divide these two polynomials. So we have r of x is 2x over x squared plus 1. And again, s of x is 3x plus 2 over x to the third plus 5. Now, I want to remind you about dividing fractions. All right, so what if you have something like 1/2 and you want to divide that by 3/4, right? Well, what do? You keep the top number the same, you change the division to multiplication, and then you multiply by the reciprocal of the second number. So you flip that bottom number. Now when we multiply across, we get 4 over 6, which of course you can reduce to 2/3. All right, now we're going to do the same thing here, right? So here we want to find r of x over s of x. So what we want to do is we want to find 2x over x squared plus 1 all over 3x plus 2 times x to the third plus 5. Okay, so the first step in this is we're going to write this as keep the top one the same, change division to multiplication, and then flip the second one. Okay, now at this point, we're going to put everything in parentheses and we're going to multiply. And of course, how do we multiply fractions? We just multiply across, right? So I'm going to have a 2x times x to the third plus 5, and then over an x squared plus 1 times 3x plus 2. And again, this is a situation where, if possible, you would want to cancel out any common factors, right? So factor as much as you can and cancel out any common factors. But here, we actually can't factor anything. So we could leave the answer like this. If you want to distribute the stuff in the top and even the bottom, that's fine too. But I prefer to usually leave everything in factored form. So it's usually easiest to leave in factored form. Okay, so that's the solution here. Okay, so the next example, now we want to talk about how we can do long division here. So here we have that the power on top is bigger than the power on the bottom, right? So you have degree 5 on top and degree 2 on the bottom. So this means that we can perform long division and end up with something that gives us a regular polynomial and then plus sort of your remainder. All right, and this is like the quotient. All right, so let's run through an example of how we can do this long division. So I want to take x to the 5th plus 6x to the 3rd plus 11x plus 7, and I want to divide that all by x squared plus 4. Okay, now the idea is that this all is going to essentially revolve around this x squared term. All right, well, not all of it, but most of it. So this is almost like we want to do sort of reverse factoring, right? So I want to think about how many times does x squared go into x to the 5th, this first term here? Well, or what would I need to multiply x squared by to get to x to the 5th? Well, I would need an x to the 3rd, right? And if I multiply x squared times x to the 3rd, I would get x to the 5th. Now, what we do next is now multiply this x to the 3rd by this x squared plus 4, and I'll get x to the 5th plus a 4x to the 3rd. Okay, now we want to subtract this thing. We want to subtract from these two terms. Well, the x to the 5th and the x to the 5th cancel, and that's good. That's what you want to happen. And then we have a 6x to the 3rd minus 4x to the 3rd, so that's a 2x to the 3rd. Right? Then we bring down our 11x, and then we just repeat this process. How many times does x squared go into 2x to the 3rd? Well, I would need a plus 2x, right? Because then I would have to go from 2x to x to the 3rd. I would need one more x, right? So we have, when I multiply through, a 2x to the 3rd plus an 8x. So I'm going to subtract that. And if I subtract the 2x to the 3rds cancel, and I'm left with a 3x. All right, and then I bring down the 7. All right, now at this point, x squared can't go into 3x, right? Because x squared is bigger than just x, right? So now we basically have it. Now we can say that our quotient is whatever's left up top here. So this is x to the third plus 2x. And then this is like my remainder. So I'm going to add that 3x plus 7 over what I was dividing by. So x squared plus 4. All right, and that's how we could perform the long division here. So whatever is sort of left over, you would write that above what your original divisor was. All right, so that's the idea. All right, and this is something that takes a little bit of practice, but once you do a couple examples, you sort of get the hang of it. Now, one thing that did come up here, but it didn't really matter, is that just notice here that there's no x to the fourth term, right? So sometimes it makes things easier to write plus 0x to the fourth. That way you can sort of keep everything lined up. Now, it didn't matter here because we didn't have an x term here in our divisor, but that could sometimes play a role. All right. Now, this theorem here says that if you have two polynomials and you want to divide them, then basically what happens is that you can either divide them cleanly, right? And that's the case where r equals 0, right? Then that means that you get a nice clean polynomial g, or there is a way that you can divide this such that you end up with a remainder where the remainder has degree less than what your original divisor was. And that's sort of what we just had happen, right? Because our divisor had degree 2 and our remainder had degree 1, right? Now, if you look at this previous one, we had P over Q equals G plus R over Q. Another way that we can say that is that if you multiply through by Q, you're going to get this. All right, so you could always say that your original polynomial is something times another polynomial plus some remainder, right? So that's just, this is sort of just another way of phrasing it. Okay, now remember in a previous video that we talked about zeros of our polynomial, right? And of course, t is a zero of a polynomial. If and only if x minus t is a factor of that polynomial. Okay, so now we're going to see how that sort of plays a role in our rational functions, right? Now, I guess one way you could think of this is that if you have p of x over q of x, and that's your r of x, you could say that if the top is 0, as long as the bottom is not 0, that allows you to say that r of x is 0, right? Because if when is a fraction equal to 0, it's when the top is equal to 0, right? So that's sort of the idea there. Okay. Let's look at example 5. So now we're going to suppose that our rational function is this thing here, and we want to know what happens as we make x near infinity and near negative infinity. All right. Well, when we looked at polynomials, we said that each polynomial sort of behaves like its largest power term, right? So we have 9x to the 5th in the top sort of being the dominant term. And in the bottom, we have the x to the 8th being the dominant term. Now, of course, if you were to simplify this, this would be a 9 over x to the 3rd. Okay. Now, if you make x large, right, what happens? Well, you could say that, for example, you'd have 9 over like 1 million to the 3rd. All right, you're taking 9 and you're dividing it by some very large number. So this is going to be a very small number. Right, and of course you could make your bottom number as big as you want, and you're going to be making overall, what's the very small numbers going towards? It's going to 0, right? So if you have a situation like this, this is going to be close to 0 if x is close to infinity or negative infinity, right? Because you're taking a number and you're dividing it by larger and larger numbers, which is overall making the overall number smaller and smaller. So what's happening there is that that's going to 0. All right, so that's an important concept. All right, we can summarize everything that's going to happen here, right? So if the degree of the numerator is greater than the degree of the denominator, what is going to happen is you're going to get something like say 9x to the 5th over x squared, right? Then you simplify that and you would end up with 9x to the 3rd. And using what we talked about in a previous video, you could say that this is going to behave in this way, right? As you increase x, you're going to increase y. As you decrease x, you're going to decrease y, something like that. All right, so that's the first case. Now, the second case is what if they're equal? What if the degree in the top is equal to the degree of the bottom, right? So that would be something like 3x squared over 5x squared. Well, if you simplify this, you're going to get 3 over 5. And that's what would happen. If you have something like this, that's what x is going to go towards as you make x go to plus or minus infinity, right? Because essentially the x's are going to cancel each other out. You're going to approach 3 over 5. All right. And then, of course, in the example that we just saw, the degree in the bottom was bigger than the degree in the top, and that's when you go to 0. All right. So those are sort of the 3 cases. Okay. So in this the 6th example, we want to know the percentage survival rate of a seedling of a particular tropical tree can be modeled by this equation, where a seedling has an S of D % chance of survival if it is D meters distance from its parent tree. Okay, so we want to know approximately what distance is the survival rate 10%. Well, if the survival rate's 10%, that means that our Y here is 10%. So we want to set 10 equal to 15 D squared over D squared plus 40. Okay, so we want to solve this equation. So what we can do is you can multiply both sides by the denominator. We get 10 times D squared plus 40 is 15D squared. And then if we distribute, we have a 10D squared plus 400 is equal to 15D squared, sorry. We'll subtract 10D squared. And then we get 400 is equal to 5D squared. And of course, once we divide by 5, okay, 400 divided by 5, I guess that would be, so I want to say that we get an 80, right? If you do 5 times 80, you should get 400. So then it looks like D is the square root of 80. All right, and since we're talking distance, we of course only want the positive square root. And of course, if you wanted a decimal for this, you could say that this is roughly 8.94. Right, so that's the idea. You could also say that this is square root of 16 times 5, which is square root of 16 times square root of 5, which is a 4 square root of 5. All right, so depending on the format of the answer that you want, either one of those would work. Okay, now in part B, let me give myself a little bit of room. In part B, we want to know what survival rate does this model predict for seedlings that grow very far from the parent tree. So this is equivalent to saying if the distance is going towards infinity, what happens to S? Okay, well, remember our S of D is 15D squared over D squared plus 40. And if D is going towards infinity, then what matters in the long run is the highest degree term in the top and the bottom. Well, if we simplify this, the D squareds cancel and we get 15. So it looks like the further away the distance from the parent tree the seedling is, it looks like the closer we're going to get to a 15% chance of survival. Right, so that's sort of the idea there. Okay, and this is a nice sort of push in the right direction to what we call an asymptote. So we say that a line is called an asymptote for a graph if that graph eventually gets to a point where you can get as close to that line as you want without touching or crossing over that line, right? So for example, right, if we look at r of x here, we know that when x goes to infinity, what matters is the highest degree term, so we get 3x to the 6th over 2x to the 6th. And of course, these cancel and we're left with 3 over 2. All right, so that means that y equals 3 over 2 is a horizontal asymptote. Okay, now if the bottom were equal to 0, that could also potentially result in an asymptote. But since the directions say find an asymptote, that's the obvious one that they're referring to, right? So 3 over 2. Okay, now in this example, same idea. We want to look at the behavior as we go towards infinity. So we want to look at the highest degree terms. And if we simplify this, we're going to get a 2x to the 4th. Now, since our degree is even and our leading coefficient is positive, this is going to behave like y equals x squared. Okay, so we know that in the long run, it's going to behave like this. So as x goes to the left or goes towards negative infinity, y is going to increase, or we could say that y goes to infinity. And of course, as x goes to positive infinity, y increases as well, which again, we could say just as y goes to infinity. Okay, so either one of those would work here. Okay, now I think this is the last example, yeah. So here, we want to discuss both types of asymptotes here. All right, so let me give myself a little bit more room. Now, you have a vertical asymptote at any value that would make the bottom 0 that doesn't make the top 0. So we need to solve x to the 3rd minus 2x squared minus x plus 2 is equal to 0. All right, well, this is something that we need to factor by grouping. So I'm going to group the first 2, group the second 2, and put a plus in between. Now, in the first pair, I can take out an x squared, and I'm left with an x minus 2. And in the second pair, again, since I want them to match, I can factor out an x minus 1, and then we'll have x minus 2 left over. So now I can factor out the x minus 2, and I'm left with x squared minus 1. And now this is equal to 0. So x minus 2 is equal to 0 when x is 2. And x squared minus 1 is equal to 0 when x is plus or minus 1. So you actually get 3 vertical asymptotes here. And I'll pull this up on a graphing calculator in just a second. All right. Now what about the horizontal asymptote? Well, that's just what we had before. That's where we look at the degrees, and we use that to figure out what our asymptote is. Well, here, the degree in the bottom, or the degree of the denominator, is bigger than the degree of the numerator. So this means that we have a horizontal asymptote at y equals 0. Okay, so let me show you what this looks like on a graphing calculator, and then we will wrap this video up. So let's pull up a new share. Okay, I want to pull up the calculator here. Okay, so you now should be seeing the graphing calculator. So let's go to our y equals menu. Okay, as soon as it decides that it's ready. Okay, so let's try this again. Go to y equals. Okay, there we go. So let's clear this out and let's put in our rational function here. So I'm going to put my top in its own set of parentheses. So the top is x squared plus 5. I'm going to close the parentheses for the top, and the bottom in its own set of parentheses is x to the third minus 2x squared. Oops. Okay, minus 2x squared minus x plus 2. Okay, so there's my function. Now, if we graph this, let's put a window just so we can see all of our asymptotes here. So -5 to 5 should do it. And then let's just make our y max and min -10 to 10 for now. Let's see what happens. So if we graph it, okay, so this is good. So you're now seeing where we have these different asymptotes, right? So we said that we had asymptotes at plus or minus 1, right? So that's where you're seeing here's your -1 right here. And then, of course, your +1 is happening here. All right. Now, you also have one at x equals 2, and that's sort of where the graph is sort of also cut off at the end there as well. And if you zoom out a little bit, let's take the window. Let's maybe take it up a little higher and graph it. You can see even better sort of where that x equals 2 asymptote is. All right. And of course, if you go to the right or go to the left, you're also approaching y equals 0. So that's the idea of the horizontal asymptote there. Okay, but that wraps up this video on rational functions. I hope you enjoyed, and I will see you next time.